Continuing with our discussion of the evaluation of limits, in this uh, section we discuss the use of the squeeze theorem. The squeeze theorem is also known as the squeeze, sandwich, or pinching theorem. So you see all these notations, these nomenclatures in different textbooks. And this is the idea. Um, we have a function, and for whatever reason, its properties are such that it's difficult to find the limit at a given point. But suppose that there are two other functions which are simpler, whose limits we know at the point, and they both have the same limit, and the values of the difficult function are lie between the values of the more complicated function. Okay? So this is an illustration of the idea. This is the sort of situation we are talking about. We have a simple function whose graph is in green. We have another simple function whose graph is in red. At the point of interest, they're both coming to the same limit. And the values of a complicated function, that's the one whose graph is in blue, though the values of the complicated function lie between the values of the two simpler functions. So then its values are squeezed between the values of the two simpler functions. Since the two simpler functions are coming together, or at least in the limit, they're coming together at that point of interest. The complicated function takes the same limit at x naught. Okay, so let's state that. Supposing you have the limit as x goes to x naught of f of x is equal to L, and the limit of x goes to x naught of h of x is also equal to L, and g of x, that's the one whose limit we would like to find. The values of g of x lie between the values of f of x and h of x on an interval containing x naught, except possibly at x naught itself. Remember, when we're taking limits, we never let x equal x naught. Then the limit as x goes to x naught of g of x will also be L. So we give a few examples of its use. Supposing we want to evaluate the limit as x goes to 0 of x squared sine of 1 over x. Now sine of 1 over x as x goes to 0 oscillates wildly between -1 and +1. So, and it's undefined at 0. Okay, so that sine of 1 over x is making this a little bit complicated. So what we do, we just consider the values of sine of 1 over x to begin with. Where sine of 1 over x is defined, the sine function takes values between -1 and +1. Now if we multiply through by x squared, we have minus x squared is less than or equal to x squared sine of 1 over x less than or equal to x squared. So we have the function of interest, x squared sine of 1 over x, and its values lie between minus x squared and positive x squared. Now limits of minus x squared and positive x squared are very easy. Right? At 0, both of those functions go to 0. Then by the squeeze theorem, the limit as x goes to 0 of this function, x squared sine of 1 over x, that will also be 0. Okay, so once again, we use the squeeze theorem to avoid thinking about the squeezed function, and we evaluate the simple limit of the squeezing functions instead. Okay, one thing that you should be careful of when you're multiplying through by an inequality, if you multiply or divide by a negative number, then you have to flip the inequalities, right? So greater than becomes less than. In this example, we don't have to worry about that because x squared is never negative. Okay, let's try another one. F sends reals to reals. The domain is the reals, the codomain is the reals. And the function is defined as f of x is equal to x squared when x is a rational number, and it's equal to 0 when x is not a rational number. Okay. Now I want to evaluate the limit as x goes to 0 of f of x. So, okay, that's a fairly complicated question. Again, one way of doing this is to try to think about what happens when we squeeze these values, between the values of two simpler functions. Okay, so let's take a look. One value that f of x can take is 0. Another value that f of x could take is x squared. Well, okay, so 0 is less than or equal to 0, and 0 is less than or equal to x squared for any real number x. We also have that 0 is less than or equal to x squared, and x squared is less than or equal to x squared. So the two values of f of x, the two possible values of f of x, are trapped between 0 and x squared. So I can write that 0 is less than or equal to f of x is less than or equal to x squared for all reals x. So now this f of x, this function, the values of this function f, which is complicated, lie between the values of two simpler functions, a constant function and a polynomial. Okay? And the limit of the constant function and the limit of the polynomial function are both equal to 0. Okay? Then by the squeeze function, the limit as x goes to 0 of f of x is also equal to 0.